Good morning, everyone. I'm excited to be here today. And my name is Wang. I go by Wang. I'm a developer advocate at Alluxio. I manage the Alluxio open source community. And along with Ziyue, we are co-presenting this paper, Data Caching for Enterprise-Grade Petabyte-Scale OLAP. And we'll present this joint open source project between the Alluxio open source team and Uber data platform team. And this project started from early 2020. It's capturing the real world challenges by Meta, Uber, and many other tech leaders in the Bay Area. And it's aiming at building a simple and highly effective approach to tackle, to use the data caching for like OLAP systems. And this open source collaboration, today I'm just going to cover the collaboration between Alluxio and Uber. And if you're interested in Alluxio and Meta in Presto, you can check out the blog and Presto paper. Okay, let's get started. And this is the agenda we're going to cover today. And I'm going to start from why we started this project and what is the problem and challenges out there that triggered this research. And first of all, let's take a look at what the Uber system looked like. So here I lay out two systems. One is the data query system, the other is data storage. Both are very business critical. And for the query system, it's powered by Presto, which is an open source distributed SQL query engine for OLAP, as you're familiar with. It's powering their interactive and also batch queries. And as you can see from the number here, it's really on a very large scale, massive number of this, the scale of the Presto fleet. And then from the data storage side, they are using Apache Hadoop HDFS as the storage engine for them. They're powering all of these different business critical analytics kind of like workloads, and it's transitioning to a higher density HDDs to save costs. And then, so with these query and storage system in mind, let's take a look at some numbers and the traces we gather from production, and all of these characteristics in the I/O perspective and data access pattern perspective. And first of all, on the left-hand side, you can see from the table, it's really like read intensive. And it's also like have like massive scale of like number of reads from like a certain amount of time. And also from the data access pattern, as you can see from the figure on the right, it's very skewed, which means they are only a small number of blocks are accessed very frequently. And then it's also like from the storage media perspective, and we can see they have like I/O throttling problem that the I/O bandwidth cannot match the HDD capacity on the data nodes. And also from the access, because they're using Apache Parquet and ORC kind of columnar file format, and it's really like for read operation efficiency optimizations. So you can see it's very fragmented, like just like a lot of small data access dominates. So because of these workload characteristics in mind, and we see like the idea of using a cache can be a very good fit here. So given our observation here, along with the collaboration like Alluxio open source community did with Meta, and we are thinking of using a very simple and flexible cache layer to solve these challenges. From the simple perspective, we want the project to be like incremental so that we can have rapid iteration and to get quick consensus between different teams, because we're working with Alluxio and working with different teams at Uber. And also we want to flexible because we not only want to address the problem today, but we also want to future-proof, and not only want to address the performance, but also want to address the cost. So we want to also consider the scalability of the system at the same time for in production. So let's take a look at what are the design requirements. And first of all, we wanted to be application agnostic, which means we don't want this cache to serve only one type of workloads. We wanted to serve different kinds of workload, at least from OLAP perspective, to serve both the query SQL query engine kind, as well as the HDFS data node. And also because we all know that fetching data over the network is very expensive and it's very slow, and like the interactive queries are time consuming and it's impact end user experience a lot. So you want to minimum the socket communication with application, and these requirements really affect our design decision. And also we want to, we know that the modern OLAP system is usually have a great usage in the memory, so that we want the cache system to have a minimum memory footprint, and also to have a single node of caching of up to a few terabytes of data in the scale perspective and in the media perspective. And we want to handle both a random and a sequential data access from the cache perspective. And finally, of course, we want it to be fast. We want it to be high performance. And these are the basic requirements that are impacting our basic design. So let's take a look at what the architecture is like for our cache system. We call this Alluxio local cache. As you can see from the diagram on the right, it's showing a flow of the Alluxio local cache. It has different components. And the main goal is to enhance the read performance, because I've showed the data and the table there. You see most of them, the requests are read requests for the OLAP system. And also, because of this characteristics, we only want the cache to handle the read requests, so all of other requests are bypassed. And you can see there is an admission controller in the beginning after the Alluxio local cache receives and request, and then it can handle, prioritize the most frequently accessed files. And also at the core, there is a cache manager, which is handling the cache process on cache hit or cache miss. If it's on cache hit, it returns the requested page directly. If it's on cache hit, it will retrieve the data from the data sources here. As I listed, there are a few different sources that we support. And then we also have implemented some very classical cache eviction policies, including FIFO random or LRU, and also can be time-based, as data privacy is really important nowadays. And the last thing I want to mention, there is a page store here to transform the file level operations into pages. And this is because, as I've shared before, the requests are usually very small. So only file level cannot meet the granularity that we want. So there is a page store to transfer the granularity. So this is basically what the overall architectural design like. And now I'm going to talk about the basic design, and these three are the designs we are doing. And first of all is that we are leveraging local SSDs, because we want to make sure the cache should not be bounded by the size of the memories. And also SSDs are usually underutilized in production that we have seen. And also, like I mentioned, there is a page-based storage. And page-based storage is because we want to have break it down into smaller pieces, more manageable, that is on the page level instead of on the file level. And finally, we have organized these pages based on a hash map that we call it an index set, so that we can quickly locate what are the data we require, right? And then I'm just going to talk about the optimization and improvements we did, and these are really tied to the production workloads at Uber. The first optimization we are doing is a cache omission strategies. We did the regular expressions or JSON format expressions. As you can see, there are lines of codes here. This is really a filtering of the cache, which means that we only have a limited petitions to by the platform owners on the cache. And with this cache admission, which is a cache filtering, and it has shown great results at Uber that we see only less than 10% of the requests that needs to go through the external storage as I show in the architectural diagram. And then the second of all, we also analyze the historical data access patterns, which means that we can access the data block hotness. So that is used in the HDFS data node local cache portion. And that one is having like even better results that only 1% of the requests needs to require the slower storage. So these cache admission strategies really work at Uber. And then the next one is about quota management for multi-tenancy. So this is to optimize in the multi-tenancy environment to ensure that it is fair and it's efficient use of resources and is making sure it's benefiting all users and maintaining the system integrity. And this is an advanced feature developed by Alluxio open source community. And this is in production at Meta, but not in Uber. So I'm not going to talk about in detail, and if you're interested, you can check out our manuscript. Now I'm going to hand it over to Ziyue to talk about the use cases at Uber.
Hello, I'm Ziyue. Nice to meet you guys. Now we'll move on to some case studies of Alluxio local cache. We will cover 2 case studies at Uber. One is the local cache embedded in Presto within compute layer. And the second is the local cache in HDFS data node within the storage layer. Alluxio cache supports various file reader classes. The data is organized into pages and can be stored in memory or files. To mitigate CPU overhead in processing complex column-oriented data files, this local cache also carries file metadata. The metadata can be stored in memory, files, or key value store. Upon cache misses, as introduced before, we employ a read-through strategy, loading data from external storage for the reader. We also have some updates for Presto specifically. For example, we just show one that called soft affinity scheduler here. For your information, Presto segments data into row groups and distributes splits among the worker nodes through this Presto coordinator. Conventionally, the primary objective of this scheduler is to evenly distribute tasks by randomly assigning splits to workers for the best load balance. However, this has proven to be inefficient for caching because it led to frequent admission and eviction of data from each worker's local cache. To address this, we have this soft-affinity scheduler to allocate splits from the same file to the same worker node. We also cover more details on how we handle the temporal inability to maintain the soft affinity. Welcome to check our paper. We evaluate Presto local cache through measuring the time spent on reading Parquet files. We obtain the results before and after the activation of caching. At Uber, this time spent on reading Parquet files can be measured or say quantified by the operator called scan filter project operator. This is a key internal phase within a Presto query responsible for data input and initial filtering. At Uber, over 97% of the queries involve reading through this operator, highlighting the relevance of this metrics. At Uber, we observed that the activation of the cache reduced the wait time by 67% for P90 and 64% for P50. We also cover a full benchmarking result in the paper. In the case of HDFS data node, we have very limited SSD space and thus only store very hot data in the cache. Take Uber as an example. Each data node has a storage capacity of 500 terabytes. but only a few terabytes of SSDs are available for caching. Thus, we have this rate limiter on each data node to avoid frequent cache admission and eviction. To be more specific, this rate limiter determines whether a data block should be admitted to the cache based on the historical data access patterns. We are also aware of an interesting trade-off here, like whether we should have local cache or a distributed caching layer. At Uber, we pick local caching because it already offers a substantial return on investment. As introduced before, we observed that a very small group of extremely hot blocks can attract a majority of the read traffic, eliminating the need to significantly scaling up or down on single node. Again, we show Uber's observation here in a 1-hour time window. Our local cache serves over 70% of the read bytes and reduced the number of processes blocked by I/O significantly. Till now, Uber successfully stores up to 1 exabyte data in high-density HDDs, achieving at least 50% TCO savings from this shift to high-density HDDs. We observe very little I/O throttling. We next introduce some lessons learned from the development and operation of the Alluxio local cache. First, our experience shows that caching metadata, like the column metadata in Parquet files, can significantly alleviate CPU overhead. For example, caching deserialized metadata can reduce CPU usage by up to 40%. We also recognized the trade-off in cache page size between read amplification and metadata footprint, and also number of requests going to remote storage. Larger page size reduce remote read requests, but increase read amplification, while smaller size lower data fetched, but increase the number of remote IOs and also enlarge the metadata footprint. So we found that 1 megabyte page size strikes the optimal balance. And for practical tuning, we recommend starting with 1 megabyte page size. Due to the time limit, we can't cover all of the lessons learned. So we welcome offline discussion here and also check our paper. Finally, we share some insights from unexpected failures encountered in the operation of local cache. First, local cache sometimes hangs on read requests due to resource contention with other applications. Implementing a fallback to remote storage has proven effective. Second, we also observed corrupted files causing SQL query failures and much lower cache hit ratios. To address this, we proactively evict cache entries upon detecting failures. Lastly, although Alluxio local cache has a set capacity, SSD can sometimes become fully utilized before reaching that capacity during ongoing operations. By caching the node space left on device exception, we initiate early cache eviction. If you are interested, welcome join the Alluxio community and talk to us. Thank you.